So today our main focus and objective should be to understand how a particular junction field effect transistor works and the advancement over junction field effect transistors are MOSFETs, MESFETs, but in our syllabus we'll be discussing till MOSFET. Our main focus will be on the construction part of it and the basic working principle and the characteristics of it. Now, when we discuss about junction field effect transistor, it is a simply bit different from transistor because in transistor both the carriers come into play when we are talking about its working. But in case of junction field effect transistor, it is usually a unipolar transistor. That means any one of the majority carrier is involved. Either it is N channel or it is P channel. That is either the junction field effect transistor basically is because of sorry it's basically because of the P type semiconductor or a N type semiconductor. Now the transistor that we have seen earlier, if you have a close look at the output characteristics of common emitter transistor, you will be able to see that the behavior of the transistor is actually getting controlled if we change the input current, that is the base current. Okay, so whenever we try to change the input current, the behavior of the transistor as per its output characteristics, we see the change at the output. But it is not the same in the case of junction field effect transistor. In case of junction field effect transistor, we will be able to change the behavior at the output by just controlling the input voltage. So it is very important observation around about JFET that these are actually voltage controlled devices, and in transistors most of the cases, if we are discussing about power transistors, there we would require huge amount of input current in order to make the transistor perform. That leads to a serious amount of power dissipation, but it is very limited in case of junction field effect transistor, because in order to bring the best out of the junction field effect transistor, we just have to apply voltage at the input, and by changing the voltage at the input we can get the output characteristics changed as per our requirement. Now the the nomenclature which says field effect, it's because of the charges that establish an electric field which actually controls the conduction path of the output circuit without the need for direct contact between the controlling and the controlled quantities. This is a very important part in field effect transistor. We will just discuss it in the later slides. Now, what is the symbolic representation of a junction field effect transistor? If we look into the symbolic representation, this is how it will look. Now if the arrows are getting into it, we usually call it N channel. If the arrows are getting out of it, we usually call it P channel. It again depends on the applied potential at the input terminal, which we usually call as gate. So in the case of transistors it was collector base emitter, but in this case it is drain given by D, it is gate given by G, and it is source given by S. Now let us have a look at the junction field effect transistor construction. Now usually if we consider an N channel type, so when we consider an N channel type MOSFET, then a slab or a portion of N type semiconductor is doped with P type semiconductor on both. As you can see on the left side we have P type doped, and on the right hand side again we can see P type is doped. So by joining these two sections with a ohmic contact, you can see the black portion is the ohmic contact. That means semiconductor is being connected with the help of a metal, hence we call it ohmic contacts. So these two ohmic contacts are again connected together and it is called the gate. And the upper portion, again it is the semiconductor part, that is the N channel, is getting connected with a metal and then with the terminal we call it drain, and at the bottom of it you can see again a metal has been deposited over the N type material and we call it source. Since we are doping a P type onto an N type, obviously there will be a flow of charges to establish the equilibrium and they will form a depletion layer or a region or a space charge region. We have already seen this in case of diodes in our earlier discussions. So simply if we see N type is being doped with a P type material, there will be a depletion region formed across it. So this is basically the structure of a it can be N channel, it can be P channel junction field effect transistor. So if you get a question like say what is a junction field effect transistor, and answer or briefly explain the construction of a N channel type junction field effect transistor, then you will have to discuss briefly what is junction field effect transistor. Then you have to discuss the construction of JFET with a suitable diagram. When you are talking about N channel, the N slab will be doped with P, and when you are talking about P channel, the P slab will be doped with two N types. So this is the only difference between the construction of JFETs of both the types that are available, that is one is N channel type JFET and another one is P channel type JFET. We are not calling it PNP here, we are not calling it NPN here, because here only the majority carrier takes place in the current conduction. Okay, so either it will be N type, the base material if it is N type, or the channel if it is the N type, then it is N channel, and if it is P type then it is P channel. Okay, now we will have to understand how this particular junction field effect transistor works. Now to understand its performance, what we need to do is we have to connect a battery. It's a variable battery or a variable source on the right hand side you can see, and we are giving it a name as VDD, but it has been connected across drain and source. Essentially, the positive side of the battery is connected to the drain and the negative side is connected to the common terminal or the reference terminal. Now, in order to understand the maximum capability of the junction field effect transistor, you need to connect the gate to the ground. You see, we have connected this particular terminal, which is usually called VGS, to the ground terminal, and the drain to source has been connected with a variable potential source, which is usually called VDD, and the drop is called VDS. So initially, when the input is connected to 0 volt and the VDS is increased on the right hand side, so the drain terminal, which is this on the top hand side, becomes more positive with respect to the ground or the reference. Now you can see the P side has been connected, both the P side has been connected to ground. So if you closely look inside the N channel MOSFET, the upper side N type is getting more positive with respect to P. So you can see this particular section, which is shown by a shaded region, which is the depletion region nearby the drain, now increases compared to the lower half, because in the lower half the P material is connected to ground as well as the source, which is connected to ground. So there will not be a massive change in the depletion region at the bottom side, rather there will be a massive change at the top of the side, because the N channel top side is now getting more positive with respect to P, which is essentially grounded. So as if I am trying to squeeze a pipe and the flow of the water is now, the velocity is increasing as I press the pipe, right? So in this case, somehow we are actually changing the resistance of this particular N channel. Fine. Now let's try to understand the characteristics of it. So as soon as we increase the drain to source voltage, the current through the device increases. Okay, so if the current through the device increases, so there is a change in N channel resistance. Fine. And on the right hand side we are increasing the voltage and we can see the current is increasing. Now till what? As the voltage is increased from 0 volt to few volts, the current will increase as determined by the Ohm's law, and the plot of ID versus VDS will appear. So as we can see it from here, that we are increasing VDS, and when we are increasing VDS, the current increases slowly as seen by this particular curve. Okay, now the plot reveals that the region of low values of VDS, the resistance is essentially constant. It's constant as VDS increases and approaches a level referred as VP. The depletion region will widen, causing a noticeable reduction in the channel width region. Now this is very important. So as the voltage VDS increases very slowly, just look before VP, this particular plot remains almost straight, which shows that the n channel resistance is almost same, but as it reaches Vp, usually Vp is called the pinch off voltage. As it reaches Vp, we can see the depletion region will widen. Now, what this particular depletion region gets widened, and there will be a noticeable change in the depletion width. The width will considerably reduce. Now, the reduced path of the conduction causes the resistance to increase. Now, all of a sudden, we can see this curve is bending. Now, this is because the resistance of that particular region is getting increased severely, and we see a curve in the graph. Okay. More horizontal the curve, the higher is the resistance. So as we approach Vp, we can see the curve is getting flattened. Okay, so it is suggesting that the channel resistance is increasing. So slowly it reaches infinite ohms in that particular horizontal region. So you can see after this it becomes saturated. So even if you increase VDS, you will see there is no significant change in the current. Okay, so this is called the saturation level. So this is the maximum current that is possible through the junction field effect transistor when the input voltage is 0. So whenever you get a current when the VGS is 0, we call that IDSS, that is current flowing through drain to source saturation. IDSS is nothing but current flowing from drain to source in the saturated level. So every manufacturer of junction field effect transistor will provide IDSS in the data sheet. Fine. So now let's see what happens when it approaches Vp. As I was discussing earlier, when this particular voltage that is connected at the output VDS almost reaches Vp, you can see the channel width has considerably reduced. Okay, and the we usually call this as pinch off. That means somebody has pinched the channel, and after that you can see even if we increase the potential, the current almost remains the same. Okay, we all know that V is proportional to I. So you can see even if we are changing V, I remains constant. Okay, so V equal to IR. Now you can imagine what's happening in case of the channel resistance. Okay, so even when the pinch off happens, there still exists a channel, and because of that a constant amount of current will be possible through it, and that will be the maximum drain to source current. We are calling it saturation drain to source current. Now this is only possible when the input voltage is 0. Now what happens if we try to increase the input potential? Now you have to remember one thing. Whenever we try to increase the input potential, we can see we have provided minus 1 volt. These are typical characteristics. You may see different characteristics for different junction field effect transistor. This is just an example. Now in this case, you can very well see that the gate potential is now negative with respect to the ground. So this is becoming essentially negative before we can provide any potential at VDS. So when we increase the input potential, that is, if when we are providing a negative potential at the gate before we are providing any potential at the output, you can see there is already increase in the depletion region at the top. This is because you are at the initial stage itself providing sufficient negative bias to this P and N region, which is actually increasing the depletion width before we can provide the output voltage. Now when we apply the output voltage and increase it, again this channel will try to increase, so we will be able to see the current as seen in the middle, that is the middle curve, where it is VGS equal to minus 1 volt. Here you can see it's increasing, and when it reaches VP, it actually is again saturated. Now this happens because already before applying the output voltage, the depletion region was already enlarged. So pinch off will happen at much earlier current, okay, compared to when VGS is 0. So similarly, when we increase the VGS furthermore, say now it is minus 2. So now before applying the output potential, the depletion region will be further more compared to minus 1 compared to 0. So when we apply the output potential, it will get pinched off much earlier compared to others. And when we provide a potential around say minus 4 volts, we can see the channel is already pinched before we can connect the output potential. So there is no current at the output. So we can say the junction field effect transistor is switched off. But if the input potential changes between minus 3 to 0, we can see the output current is changing as per this particular curve. So we always have to remember that to make the particular junction field effect transistor work, if it is an N channel, then we'll have to provide a negative potential at the input, and if it is P channel, we'll have to provide a positive potential at the input, that is the gate to source voltage, and then we will be able to get this particular characteristic curve. So it is always evident, and it is evident from the graph, that the output characteristics are now getting controlled by change in the input voltage. But it was not the same in the case of transistor. When we are talking about transistor in CE mode, CB mode, CE mode, the output characteristics was controlled by IB, that is the base current, and in CB mode the output current was, that is IC, was controlled by IE, that is the input current. So comparing those two, we can say that the junction field effect transistors are voltage control devices and the transistors are current control devices. Okay, so very important part that is used and actually used as an application of junction field effect transistor is VVR. VVR is called the voltage controlled resistor. Now what is this? Now the region to the left of pinch off locus is referred to as ohmic or voltage controlled resistance region. So what is it? If we talk about the left region of pinch off locus, The left region, as you can see from the dotted line, the locus of pinch of value, this is the dotted line and it is called the locus of uh, pinch of line values. Here we can see the left hand side to be the ohmic or the voltage control region. Fine. In this region, the JFET can actually be employed as variable resistor, and this particular region is being exploited in many applications where a very important application is automatic gain control. Now, automatic gain control is always used in most of the audio applications. See what happens is, when we talk about automatic gain control, in automatic gain control, we can take an example of an audio amplifier. Okay, so sometimes what happens is you are hearing a sound using your earphone, and there are certain in certain movies you will hear that apart from having a voice conversation, you may see a effect being played at the back where the sound is much greater compared to voice, and sometimes you may see in war movies that you have an explosion at the back, but those explosions create a huge powerful sound. But when you hear that using your ears, you will be able to see that it is almost constant to your ears. Fine. And whenever somebody is talking in the microphone, even if he or she is pitching up or pitching down his voice, you will be able to see that okay, the sound is almost constant. This is actually done using automatic gain control in amplifiers. In automatic gain control, the speakers actually do not give out any noise just because of getting a high input at a high powerful input. So it doesn't change the output a lot, but actually this circuit reduces it and controls the gain of it. Okay, so this is very important when we talk about amplifiers, though it is not in your syllabus, but if we can study those circuits, you will be able to appreciate how this junction field effect transistor works as VVR. So you will have to remember that when we are talking about VVR, which is usually called voltage variable resistor, in many cases you can call voltage controlled resistors, it is actually the left hand side of the pinch off locus, and we usually the ohmic region, which is used for voltage control as a voltage control region. Okay, now let's move on to the next section, which we call as the transfer characteristics of junction field effect transistor. Now in case of transfer characteristics, we can see we are just plotting another side of the output with respect to the input voltage. Now you can see on the left hand side we have plotted VGS, and on the right hand side we have plotted VDS, the output versus the output current, and on the left hand side we have plotted the input voltage with respect to output current, that is ID. So it is evident that when the VGS is at -4, obviously there is no current. So this is the point on the curve. Now again, when the VGS is -3, we can see there is a marginal increase in the output current. So this is the point, and this is the point where it is -2, and this is the point when it is -1, and we get maximum current when VGS is 0. So joining all these points will provide you the transfer characteristics. So the transfer characteristics is possible if we plot the output current with respect to the input voltage of any junction field effect transistor or any MOSFETs. So it is again the relationship between the ID and VGS is provided by a Shockley equation, and it is given by this, where ID is the drain current, IDSS is the IDSS and VP, and VGS are the controlling parameters. Fine. So based on this equation, we either get the maximum drain current or the minimum drain current depending on VGS. Okay, so this is called the Shockley equation, and this is only valid with respect to junction field effect transistors. So this is all about junction field effect transistor, its construction and the characteristics. Okay, now we will move on to the next part, which is called MOSFET, or the metal oxide semiconductor field effect transistor. Now this is widely used everywhere, whether you are talking about your computer SMPS, whether you are talking about the transistors used in your CPU, in your computer, in your laptops, whether you are talking about inverters, whether we are talking about amplifiers, everywhere we have replaced transistor with MOSFET. Now the reason behind it is easy. It can be easily fabricated. It can be fabricated in a very small scale. It can have very low power consumption, and it is very stable, and the longevity of the device is more compared to transistors. Now, but again, one thing, MOSFETs are very susceptible to static charges, so it is very important that we practice good precaution before we use the MOSFETs in the industry. Now, what is the construction of the MOSFET? You can see the MOSFET is basically having two types. One is called the enhancement type MOSFET, and another one is called depletion type MOSFET. Now first we will talk about depletion type MOSFET. Now again, this MOSFETs are of two types. It can be N channel, it can be P channel. Now N channel MOSFET will basically have a substrate, or that is the base, which will be of the opposite of the channel that we are fabricating. That is, if we are talking about N channel, then the opposite type is the P type. So P substrate will be there, and above which we will construct an N channel. So this section, which is a rectangular type of a section, is called the channel, and there are two sections which are usually looking like a well, are the drain and the source. Fine. Now just above this there is a thin layer of silicon dioxide. Now this is a dielectric, and silicon dioxide, a thin layer of it is formed over this, and then there are certain techniques used to remove this section and join with a metal contact, usually shown here by a black layer, to the respective regions. That is the drain and the source. So with the metal contact we have a terminal called D, with the metal contact we have terminal called source. Now remember, there is a insulator which is between the channel and the gate. So gate is now not directly connected to the channel, okay, but it was not in the case of N-channel JFET. JFET was, the gate was directly connected to the P type if it was a N channel, or if it was a P channel, the gate was directly connected to the N type, but not here. You can see the gate is being insulated with an SiO2 layer. Okay, so since there is an insulator between the gate and the channel, the resistance between these two is very high. It's almost infinite. Almost infinite. In ideal case it is infinite, but in practical cases it's very large. It's in thousands of megohms, in mega ohms. So it's very large. So whenever this particular device is connected in a circuit, you will not expect any current to flow through this. Okay, so this is a very important observation with respect to MOSFET. Here we cannot, here the system will not, or the MOSFET will not draw any current from anything that is being connected at the input of it. Okay, so there is almost no current required to drive this particular device. That is why nowadays the systems are becoming very small, because we are advancing in MOSFET technology, and because of MOSFET technology the portable devices like mobile phones, your tablets, the laptops nowadays can run longer on batteries. It is because of this particular devices. But again, there is a trade-off. Whenever you gain something, you have to lose another thing. Comparing MOSFETs with transistors are quicker, but MOSFETs are not that quicker. Okay, so if we use transistors as switch, they work rather faster compared to MOSFETs. But nowadays we are having very good MOSFETs, hence their capabilities have also increased. So one or the other we have to trade off something to achieve something. So we have trade off speed with respect to power consumption. So whenever a device is constructed out of MOSFET, it is the reduction in power consumption. Okay, now let's try to understand the working of it. Now again, if we try to understand how it is going to work, we will have to, usually in MOSFETs, I just forgot one thing to tell you. Usually here we can see there are 4 terminals, right? Drain, source, gate and substrate, which is given by SS. But when you get when you buy a MOSFET, you will see there are only 3 terminals, that is drain, gate or source. Internally this is connected to the reference terminal, which you can see here. It is usually connected internally to the reference terminal. Okay, so we will get only 3 terminals at the output. Now how this particular thing is working, when we are talking about the functionality, so study of it again, if we connect this to the ground, that the input to the ground, and a potential at the output, here we can see the gate to source voltage is set to 0 volt. Okay, by directly connecting it to the ground, also connecting the substrate to the ground, and also connecting source to the ground. Okay, now the output is connected to VDD. Now usually what happens, since this is at the positive potential, it will try to attract the electrons towards this side. Hence, there is a current flowing through the channel, and the conventional current will definitely flow in the reverse direction, because if the electrons are flowing from bottom to top, then the conventional current is flowing from top to bottom. So, when VGS is 0, the maximum current that we will get is IDSS, similar to the junction field effect transistor. Now, the more we increase the potential, what happens is this particular side of the MOSFET slowly gets pinched off, because this section will be more reverse biased with respect to the bottom section. So this will get pinched off earlier, and when we apply a negative potential at the input, what happens is a negative layer will be formed here, because we have a dielectric at the middle. So if there is a negative layer formed here, it will push the electrons back and it will allow the holes to reach here. So it will narrow down the channel further. So when we have not connected VGS, we can get the maximum current by changing the VDD till the channel pinches off. But before we apply the output voltage, if we try to increase the input potential, what happens? It will initially squeeze the channel and the pinch off will happen much earlier or below the IDSS current, as it is evident from this particular graph. Okay, in this particular graph you can see the VGS, when it is 0 we get the IDSS current, and when it is negative, slowly the current gets reduced, the maximum current gets reduced, and at a particular input voltage when it is completely cut off. But there is an interesting fact here, which is if we increase the gate potential, then we can see a current which is more than the IDSS, that is more than the saturation current. Now this usually is called the enhanced region. Why will it happen? Now if this particular input is positive, then there will be a positive layer here which will push the the holes from here to here, but it will attract more electrons from here to here. So it will increase the width of the channel. So it will require more output potential and more current will be available to pinch it off. So we can say that this particular section gets an enhanced when we increase the base potential beyond IDSS. ID can be achieved, and this ID is achieved when this particular depletion type MOSFET is worked in enhancement region. Okay, so this is evident from this how that particular thing works. So when a negative potential is applied to the gate, it will pressure the electron towards p type, which I was just telling you in the last slide. So when we apply a negative potential here, a negative layer will be available here and it will push the electrons this side. Okay, and it will attract the holes towards this side. So it will reduce the channel. But the reverse will happen if we provide a positive potential here. It will have a positive layer here, and for that it will push the electrons back. It will push the holes back and and electrons will be attracted towards this region. Hence it will marginally increase the width of the channel. Okay, so there we can see a marginal increase in the output current, that is IDS. So this was the construction and the working principle of depletion type MOSFET, and you can see the symbolic representation of the depletion type MOSFET is this, but please have a very good look into this particular symbolic representation. See, if it is a depletion type of a MOSFET, you will be able to see a continuous channel between S and D, and if substrate is internally connected, then this will be the symbolic representation, and usually this is the symbolic representation which is given at the bottom is used. So when the arrow is getting into it, it is N channel, and if the arrow is getting out, it is P channel. But remember, this is a depletion type of a MOSFET and it is having a channel already built inside it. So there will be a continuous channel shown by this black line, okay, between D and S. But since this channel is not directly connected to the gate, see, there is a gap between gate and the channel, showing that there is a insulator between these two. So this is the symbolic representation of depletion type MOSFET having either N or a P channel. Now let's see what is an enhancement type MOSFET. Now the construction is bit different with respect to the depletion type MOSFET. Here you can see, though I am talking about N channel, but see, there is no channel. So what is the construction of this? It will have a P substrate. It will have one N region acting as depletion region. As the drain region. It will have a region, N-doped region, which we will call as source. Both are connected with the terminals D and S, but here there is no channel between the drain and source. So initially this particular device will be off. So the primary difference between depletion type and enhancement type MOSFET is the availability of the channel. Now when we make audio amplifiers or amplifiers which require a constant channel, we go for depletion type MOSFETs. But when we are talking about switch, we usually consider enhancement type MOSFET, because in a by default state there is no channel. So even if you apply an output voltage, you will not get any current flowing through it because there is no channel between drain and source. So you will have to create the channel before we can start working with it. So how to create the channel? When we apply positive bias to the gate, between gate and the source, what happens? We have a positive layer at the dielectric. So what will happen? It will try to attract the minority carriers, which are electrons in the P substrate, towards it. So when we keep increasing VGS, there will be a time when a channel will build up joining the drain and the source. The moment the channel is built up, the potential at which the channel gets built up, we call it threshold potential. We call it threshold potential. So before you can make this particular MOSFET work, you will have to provide a potential which is above the threshold potential, so that the current starts conducting between drain and source. Okay, so this is the main difference between a particular depletion type MOSFET and a enhancement type MOSFET. So in enhancement type MOSFET, until and as you can see the characteristic curve on the left hand side, see there is a potential Vt given, Vt, which is 2 volt. So Vt is the minimum threshold voltage that you will have to provide, otherwise this particular MOSFET will not conduct current. So you can see when VGS is greater than 2 volts, you can see there is a marginal increase in the drain current, drain to source current. So the more we increase the VGS, the more we get the current flowing through it, because the more we increase the VGS, the more will be the width of the channel and there will be more current flowing through this particular device. So in case of enhancement type MOSFET, we will always have to remember that to make this particular device work, we will have to provide a input potential which is greater than the threshold voltage. But it was not in the case of depletion type MOSFET. Depletion type MOSFET was already having a channel inbuilt into it, and it was able to conduct in the enhancement region also. But this particular MOSFET can work only in the enhancement region. It doesn't work in the depletion region. Okay, or the depletion mode. See why? Because we are only considering the positive potential. You see, we are considering n channel type MOSFETs only. But in case of the previous example, when we were talking about this, which was a depletion type, it used to work in the enhancement zone also, but it was also working in the depletion mode. Fine. But in our case here, we can see in the characteristics, it is only working in the positive domain, not in the negative input voltage. So it is only working in the enhancement region, enhancement mode, and hence we call it enhancement type MOSFET. Okay, so now let's see the symbolic representation of this. Now it's very interesting, because you see the difference between the previous symbol and the symbol is, see, by default there is no channel. So you can see D and S are not connected, these are broken, showing that this is a enhancement type MOSFET, it's not a depletion type MOSFET. So whenever you are going to use this, always look into the symbolic representation properly. Okay, so if you choose an enhancement mode for a audio amplifier, it will not work properly, it will not work at all. Okay, but you will have to choose a MOSFET which is a depletion type MOSFET, so that it can be used for a continuous amplification. But when you are making any circuit which is having a depletion, which is having a switching characteristics like digital circuits, there you will need an enhancement type MOSFET which can easily switch between a particular potential to a zero. I mean, you may require certain current or you may not require some current. So there will be availability of channel or there will not be availability of channel to cut off the transistor. So this is the very important part that we discussed in enhancement type, and this is the transfer characteristics. As it is evident that initially when it is below the threshold voltage, there is no current flowing through it, but as we increase the gate potential, we can see the current is increasing. See, this is the difference between the transfer characteristics of enhancement type MOSFET and depletion type MOSFET. In depletion type MOSFET, it was like this, it used to go like this, but in enhancement type, the transfer characteristic is like this. So these are the important features that are of a enhancement type in channel MOSFET. Also remember, if we are considering P type, P channel MOSFETs, everything will be just reverse of it. All the potential, everything will be just reverse of it. But the explanation remains the same. So okay, um, this was the topic for today. I hope the lecture was bit clear about JFET and MOSFET and the comparison between it. So now I will be happy to take the questions. Anybody?